So far in this series, we've looked at the genetics of drug abuse, how drugs affect the brain, and what motivates substance abusers to continue to take drugs.
In this video, we're going to look at how the brain fights back against the effects of different drugs and what happens to our brain as a result of chronic substance abuse. As people begin to chronically abuse drugs, they start to experience changes in their brain chemistries. Depending upon how much, how often, and which drugs a person uses, the constant actions of these drugs on the brain will impair the brain's ability to respond and function normally. Over time, the effects of drugs and the resulting changes in brain chemistry can cause a wide range of unpleasant experiences, ranging from temporary effects to permanent damage.
Drugs are chemicals that cause changes in our body by interfering with how the brain functions. Sensing this interference, the brain tries to counteract the drug's effects so it can continue to function as normally as possible. But before learning how the brain works to protect itself from the presence of drugs, let's first review information from earlier programs about how our brain functions under normal conditions and how different drugs act on the brain to produce their effects. As we've previously seen, the human brain is made up of many millions of cells called neurons, which when functioning normally, use a combination of electrical signals and chemical messages to form a complex communications network. Although the neurons come very close to one another, they never actually touch. These close areas between neurons are called synapses, and the gap between two neurons is called a synaptic cleft. The neurons communicate with one another by sending chemical messengers across the synaptic cleft. These chemical messengers are called neurotransmitters. When a neuron receives neurotransmitter signals from its neighboring neurons, it then sends a small electrical current down its axon to a synapse. This causes the release of neurotransmitters into the synaptic cleft. The neurotransmitters then flow across the synaptic cleft, carrying their chemical messages to a neighboring neuron. The likelihood that a neuron will fire depends upon the balance of positively and negatively charged particles they contain. These electrically charged particles are called ions. Neurons containing more positive ions are more likely to fire. Neurons containing more negative ions are less likely to fire. Because different neurotransmitters send different messages, some neurotransmitters increase while others decrease the firing rates of neighboring neurons. Neurotransmitters that increase or speed up firing rates are called excitatory neurotransmitters. Neurotransmitters that decrease or slow down the firing rates of neighboring neurons are called inhibitory neurotransmitters.
By using a complex system of neurons, neurotransmitters, and ions, the brain is able to control everything we do. For the brain to function properly, neurons must correctly send chemical messages to one another in the form of neurotransmitters. This can only happen if the neurons contain the appropriate balance of positive and negative ions. So now that we've seen how our brains function under normal conditions, let's take a look at the impact of different drugs and how they act on the brain to create a fantasy world of false messages and faulty communications.
Once a drug reaches the brain, it interacts with specific sites on neurons, and depending on which drug it is, it imitates in a specific way the brain's naturally occurring neurotransmitters. In most cases, neurons cannot tell the difference between drugs and real neurotransmitters, and respond just as if the correct neurotransmitter messages are being sent, when in fact this is not the case. And because drugs imitate neurotransmitters, but are not exactly the same, this causes malfunctions in the brain's normal communication process. Different types of drugs mimic different neurotransmitters. For example, cocaine, amphetamine, and other stimulants mimic the neurotransmitters dopamine, norepinephrine, and serotonin. Tranquilizers like Valium and Xanax and barbiturates mimic the effects of the neurotransmitter GABA. Opiates, including heroin, methadone, and codeine, imitate the brain's own internal opiate-like neurotransmitters which regulate pain, and THC, the active compound in marijuana, mimics a recently discovered substance in the brain called anandamide, which is involved in regulating nausea and pain. As we saw in an earlier program, stimulants like cocaine and methamphetamine work by blocking an important process called reuptake. When a neuron's electrical signal reaches the synapse, it causes neurotransmitters to be released. These neurotransmitters bind to receptors on neighboring neurons and transmit their chemical signals. Once the message is delivered, the neurotransmitters are rapidly released from their receptors. The neurotransmitter molecules are then quickly cleared out of the synapse through this process called reuptake. During reuptake, the neurotransmitter molecules get recycled and taken back up into the firing neuron, where they can be made ready to be used again. Almost all stimulant drugs work primarily by blocking this reuptake process. When the reuptake process is blocked, these neurotransmitters are forced to stay out in the synaptic cleft, where they then transmit their chemical signals over and over, making their messages much stronger than normal. Tranquilizers and barbiturates, which make up most of the depressant class of drugs, affect neurotransmitter function in another way. These drugs bind to receptor sites on the GABA channel just like the real GABA neurotransmitter molecules. By doing so, they cause the GABA channels to open more often and for longer periods of time, with the result being more negative ions entering the neuron and less brain activity. Like the depressant drugs, opiate drugs like heroin, morphine, codeine, and Vicodin also bind to receptor sites and mimic the effects of neurotransmitters. However, opiates bind specifically to brain receptors that control our ability to experience pain and pleasure. In so doing, these drugs directly block the perception of pain and enhance the perception of pleasure. So, as you can see, each of these classes of drugs has their own specific way of interacting with neurons, and as a result, has its own set of behavioral effects. We've been focusing on short-term or acute effects of drugs, but what happens to our brain as we continue to take drugs over weeks, months, and even years? How do we become physically dependent on drugs? How long do drug-related changes in our brain chemistry last? And how does the process called homeostasis work to counteract the effects of drugs and help to protect the brain? The answers to these questions lie just ahead as we now explore some of the many consequences of chronic drug use. In response to the continued presence of drugs as a result of chronic drug abuse, the brain protects itself by taking a series of countermeasures so that it can continue to operate as normally as possible. Ironically, while these countermeasures are intended to protect us, for chronic drug abusers, they can actually make abstinence more difficult. To find out more, let's take a closer look at how the brain adapts to the presence of different drugs, beginning with a concept known as homeostasis. One of the most amazing aspects of the human body is its ability to adapt to changes in the environment that may threaten its normal function. When we take drugs, their presence interferes with the normal functioning of the brain. Sensing this, the brain attempts to counteract this interference so it can continue to function. The technical term for this process is homeostasis. Let's examine the process of homeostasis as it relates to different types of drugs, including stimulants like cocaine, depressant drugs including tranquilizers and barbiturates, and opiates such as heroin. We know that the brain uses a combination of electrical signals and chemical messages to form a complex communications network. When we take drugs, these substances begin to impair our brains by disrupting the communication process among neurons.
Homeostasis is an important weapon that the body uses to adapt to the effects of drugs. But as we're about to see, because it is so effective, homeostasis can actually make it more difficult to achieve abstinence.
Homeostasis is what leads to three important and very negative effects of drugs: tolerance, sensitization, and withdrawal. Homeostasis provides the biological basis for how cocaine abusers develop sensitization to cocaine, and why heroin abusers develop tolerance to opiates when they continue to use these drugs. and why they experience withdrawal symptoms when they quit taking these drugs. The most common definition of tolerance is when a person has to take more and more of a drug to reach the same level of intoxication. In other words, a person who is tolerant to opiates gets less of an effect from the same amount of heroin than someone who is not tolerant. The unfortunate result is that tolerance makes it easier to take more of a drug, while at the same time making it difficult to take less. The opposite effect from tolerance is called sensitization, and this is what is experienced by chronic stimulant abusers. The most common definition of sensitization is when a person has to take less and less of a drug to reach the same level of intoxication. In other words, a person who is sensitized to cocaine gets more of an effect from the same amount of this drug than someone who is not sensitized. Sounds like a good deal, doesn't it? Spending less on cocaine to get the same high? Unfortunately for cocaine abusers, some parts of the body sensitize more rapidly than others. For example, it appears that the heart sensitizes more quickly to cocaine than the brain. So the same rock of crack that got you high last week might give you a fatal heart attack the next week. It's a tragic story that we have heard told in the news far too many times since the rise in crack use that began in the mid-'80s. In the case of depressant drugs such as barbiturates, benzodiazepines like Valium, and opiates such as heroin, homeostasis makes the neurotransmitter receptors on nerve cells less responsive, so it takes more and more of these drugs to create the signals that release more dopamine in the reward pathways. Over time, then, the same amount of drug produces less and less of a reinforcing effect. So to get the strong reinforcing effect they are used to, individuals who are tolerant have to keep taking more and more of the drug. This begins a dangerous cycle of more drug use causing more tolerance, which leads to more drug use, which causes even more tolerance, which leads to, well, we know where this cycle leads, and it's not good. This cycle eventually causes the brain to lose its sense for where its chemical equilibrium should be. At this point, the brain can actually require the drug to function normally. This dependency is so strong that a sudden withdrawal from the drug will cause the brain to malfunction. During withdrawal, these effects tend to be the opposite of a drug's regular effects on the brain. So for example, once the brain has adapted to the depressant effects of depressant drugs, when the drug is withdrawn, the brain becomes overactive and its neurons are now much more likely to fire. Similarly, once the brain has adapted to the excitatory effects of stimulant drugs like cocaine or amphetamines, when the drug is withdrawn, the brain becomes less active than normal, and its neurons are now much less likely to fire. The technical term for these overactive or underactive effects is called a rebound effect. The rebound effects that occur in abusers of depressant drugs range from uncomfortable to dangerous overstimulation of the brain. The rebound effects that occur in abusers of stimulant drugs are not typically as immediately life-threatening, but can be dangerous in other ways. For example, stimulant withdrawal can cause serious depression and frequently causes insomnia and irritability, which can last for several months.
The effects of withdrawal from depressant drugs can be very serious and dangerous. These withdrawal effects can include muscle tremors and sometimes seizures, confusion, disorientation, and hallucinations, excessive arousal and agitation during the day and sleeplessness at night, as well as mood swings and severe drug cravings.
The dangers from the most severe withdrawal symptoms, such as seizures, are typically over within a week or so. However, it may still take several weeks for an individual to start thinking clearly again and for his or her depression to lift.
So, while recovering from the initial withdrawal effects of drugs may take a week or two, other symptoms such as cravings, mood swings, irritability, and sleeplessness may linger for months.
We've learned that drugs have many different chronic effects, and that while the brain recovers from some of these effects in just a few days, it takes weeks and sometimes several months to fully recover from the effects of chronic drug abuse. We've also discovered how the brain adapts to chronic drug abuse by changing its chemistry, and that sometimes the adaptation is so severe, the brain can actually require the drug to function normally. Lastly, we've seen that chronic drug abuse and the brain's use of homeostasis to protect itself from the drug is what leads to the development of sensitization, tolerance, rebound effects, and withdrawal symptoms.
Fortunately, given both time and abstinence, most of the changes in brain chemistry caused by chronic drug abuse can be reversed. The bad news is that some chronic drug abusers can suffer permanent impairments to their thinking and memory. Because of the brain's unique ability to adapt its chemistry, it is capable of successfully responding to the effects of drugs through a process called homeostasis. But just as with homeostasis mechanisms in other systems of the human body, there are limits to the brain's ability to respond to chronic, heavy drug abuse. By exceeding the body's ability to respond effectively, drug abusers become at risk for a variety of neurological and other medical problems.